Howdy, folks. I don't know why I always say howdy, but it's what I do, apparently. So, anyway, this time we're going to talk about minimums, cutoffs, and expectancy tables. Essentially, because last time, as you may have recalled, hopefully, I talked about how for domain reference testing and criterion reference testing, you often will have to make a judgment on whether someone knows enough or not. Like, what is the cut point for an A versus a B and things like that. And so here I'm going to talk about one way to look at these to develop cut points. And we'll talk about expectancy tables and a couple other things. There's a lot more detail in the book. I encourage you to check it out. I know the book is ancient, but I think it does a pretty good job. Come on, slides. Okay, so how do we decide what cutoff scores for mastery testing do we use? How many and what kinds of test items do we need to demonstrate mastery for a given field? So the answers to these questions and slightly better reiterations of those questions can be tackled a ton of different ways. But there's really big pushback from all these ways that I will talk about in a bit. So argue that if these cut points are strictly followed, important information about an individual's performance relative to others is lost. And another criticism is, although this approach has value with respect to the assessment of basic knowledge, skills, or both, it has very little meaning at the upper level of knowledge and skill. So while this approach is clearly meaningful in evaluating whether pupils have mastered basic reading, writing, or arithmetic, how useful is it in evaluating doctoral level writing or math? Not very. But so how do you identify standalone originality or brilliant analytic ability? Which is not stuff of criterion, that's just, you can't use this for that. There's a reason why dissertations and things like that are evaluated by other experts without a test. It's essentially an oral exam to demonstrate that. You can't really make a test about a new thing that that person has just developed because only they can make the test. But anyway, so it's hard to do in criterion related testing. In contrast, in theory, brilliance and superior abilities are recognized in tests that employ norm-based testing. In theory, that these are the folks whose scores trail off way to the right, past the third standard deviation. Maybe. Although, frankly, there are some limitations. Like, if I were to take the SAT now, I'd do garbage because I don't use those skills directly anymore. But let's back up. So, from a practical standpoint, these are just two ways that why? Okay, well, apparently this is where we're going to go. There are lots of pitfalls in how to determine this. Apparently, I did not write in my notes how we can do this. There are various ways, including expectancy tables, which I'm going to include in the next slide. Because here, apparently, I decided that I just want to talk about the pitfalls. Because it is a judgment call on what the threshold is. Okay, so let's talk about an expectancy table. Because this is an actual way to show the relationship between two tests. Because your goal or criterion and outcome. So an expectancy table provides the probabilities that indicate that a student achievement on a given test will behave in a certain way in some other situation. Often these are used in schools, in testing, where in this illustration I've got looking at 7th grade IQ scores and eventual graduation of college. And so as we can see with the 7th grade IQ performance below 85, very few graduated from college or graduated from high school. Again, this is about performance, not actual ability. Versus, and these are a little out of date. This is from this data is from 1949, because it was most readily accessible. I push all these numbers up, percentages up, versus someone with an IQ that's approximately average. They've got a graduation rate of about 70%. Those in the above average, the one between a third and a standard deviation above average, will graduate 80% of the time. Those with an IQ of 1 standard deviation or above are going to graduate 90% of the time. And so this gives you some sense of what a score looks like and its relationship to other outcomes. And it's a way to kind of select a criterion point. So often teachers use this information to help predict performance on another test. Eventually, I'm going to work through an example using slightly more modern data, using the Florida CAT, whose acronym I didn't spell out here. Yay! Okay, but anyway, so here the percentage, are we gonna, oh no, we don't. Oh, this is great. Okay, so here we indicate the probability of attaining a score based on performance of another score. The percentage doesn't guarantee success. They're only probabilities. So this kind of test table can answer questions like, how likely is it that a student from a particular school FCAT score band will attain a certain level on this other Florida-based testing? Florida has publicly available data. That's why I'm using it, even though I don't know anything about Florida. But yeah, so this information can be helpful for teachers to give differentiated instruction to address academic needs of individual students. That's kind of the idea here, as I've illustrated here. So if you get an 83 percentile for this student, so just here's some data for class. 83 percentile for this Florida test, scored a 4 on this achievement level, versus someone in the 9th, and we're gonna clean up this data. And but here's our raw data. So next, what we're gonna do is for each score, we are going to count the number of students at that SSS level. So for example, that student with an 83 would be counted under the 4th level. So notice that the percentiles are ranged here. Frankly, they're ranged because we have a small sample and we need to be efficient. But converting those numbers, we can see kind of a pretty solid relationship. So on your base percentile scores, those that scored in the 25th percentile and below seem to perform way lower than those in the 70th and above. That's the basic idea. Okay, so now what we do is we sum the rows and the columns. For example, in row, for the percentiles between 51 and 75, there are 6 cases. Then we look at the percentage of each cases for each cell. So in that same example, we essentially, so 5 out of 6 scored at the 3rd reading level versus 1 out of 6, so 17% scored at the lowest reading level. And so we've detailed all the totals here, and you can fill in the rest of them. Obviously, this is a really tiny sample. So you wouldn't want to say that 100% of students will get this reading level 2 based on their test performance, because at that 26th to 51st level, because it's one person. It's not a great sample. However, for my illustration here, it's got to do. But the bigger your sample is, the better these, and more spread out, the more data you have. But this is the basic idea. And so what this does in terms of interpretation is the percentage indicates the probability of attaining a score based on the performance of another test. This is not a guarantee, they are probabilities. They answer questions like, how likely is a student with a particular score will attain a certain level on this other test? But this information is still helpful, even though it's not great. Bigger samples better for this kind of thing. But it's still something to give you a sense of what the relationships are and to give you some sense of what would happen if you used various criteria. Cool. So that's it for minimums and cutoffs and expectancy tables. So I'll see you later.